Hello, geometry friends. We are going to talk about topic 3 today for Unit 6, about circles. And in this topic, we're going to look at finding lengths of segments that are in and around circles. Now, to do this, we're going to kind of relate this back to something that we learned in our last 2 units ago with similarity, and that we need to come up with a way to compare these segments in and around circles. So for example 1, I'm going to look, it says we have a circle called circle A, and that segment CB is a tangent, and secant CFE are drawn. If CB equals 6.8, so that means that the length from point C to B is 6.8, and CE is 11.6, so the length from C to E, you're going to use the bracket right here, is 11.6. Then let's find the length from C to F. So we need to come up with a way to compare, if this length of the tangent is 6.8, how does that help me figure out the length of what this little piece of the whole secant is, this part from C to F? And believe it or not, there is a way to compare them, but it's hard to see it yet based on what I have. So what I'm going to do is I'm going to just add a couple of chords to my diagram, and then by adding the chords, I'm going to create some triangles. So I'm going to go to my shape tool here, and let me use a line tool. I'll just add some black lines to this, and I'm going to draw a line to connect points that already exist from point B to point E. Okay, so now you see, by doing that, I've made one triangle in the diagram, where I have side CB as a side of that triangle, side CE as a side of that triangle. So there's one triangle, but again, having just one triangle doesn't help me see any kind of relationship there. So I'm going to draw another segment, another chord, and the second chord will create not just one but two triangles. So I'm going to connect the point B to the point F. Now, so now I have not one, but actually 3 total triangles. I have a triangle from C to B to E, the big one that I started with, and then I just created 2 more, CBF and BFE. And so there's a total of 3 triangles here. Now, you might be thinking, okay, so why bother drawing these extra lines? Well, actually what it does is it allows me to compare a couple triangles and say, well, if I know something's true about these triangles, then maybe I can figure out something about what the relationship in their lengths are. And to me, just looking at the 3 triangles, it doesn't look like any of them are congruent to each other. But because none of the 3 have the same size, but they might have the same angles, and therefore they could be similar to each other. Now, if you can have a triangle that sits inside of another triangle, then we know we at least have one angle that's the same. So if you take a look here, let me go back to my shape tool, and let me choose a color. I'm going to go with yellow here for 1. So you see how the triangle that goes from C to B to F, that I'm going to trace in yellow right here, that triangle. And let me get another color here, about pink. I'm going to go with a triangle from C to B to E. Do you see how those 2 triangles share the angle C? So at least I know that the angle C that's in yellow is the same angle C that's in pink. All right, so if at least those triangles have one pair of congruent angles. Now, if I can prove that they have a second pair of congruent angles, then those 2 triangles that I just traced would have to be similar to each other. And if the triangles are similar, then I know that their corresponding sides would be in proportion. And ultimately, that's the idea, is I'm trying to figure out a way to compare the lengths of these segments that I was given in the first place. So I know that I have a pair of congruent angles. Let me use this orange color. I have this angle right here is congruent in both triangles. Okay, now what other pair of angles has to be congruent? Is there another pair of angles that I can prove are congruent? Now, in topic 2, we learned about different angle relationships. And there was 3 of them that we learned that were new to circles. There was the central angles, there was the inscribed angles, and there's an angles formed by tangents and chords. Now in this picture, there are 0 central angles because A is the center of the circle and I have no angles formed at point A. So there's 0 of those, but do you have any inscribed angles? Yes. This angle at point F is on the circle, so there's an angle right here from B to F to A is inscribed. FEB, E is on the circle, so FEB is inscribed, and so is FBE, the other way around. This point B is on the circle, so I have 3 inscribed angles. This triangle from F to B to E, that triangle is inscribed in the circle, so all 3 of those angles are inscribed angles. Okay, but there was that. We have inscribed angles. Do you have any angles formed by tangents and chords? And yes, because we have a tangent from point C to B, then where point B is on the circle, you see how there's a chord from B to F and there's a chord from B to E. So there are 2 examples of tangent and chord angles. Now, I'm going to highlight something here, and then I'm going to erase it so that my picture doesn't get too confusing. But how about I'll try the green color. And do you see how the angle that's formed from the tangent CB and the chord BF, this angle that's right here, do you see how that angle intercepts the arc from B to F, right? So that's the intercepted arc by that tangent and chord angle. So here's what I know is true. I know that that the angle CBF is equal to 1/2 of the arc from B to F, because that's the relationship that the tangent and chord angle has with that arc. Now, down here, I also know that, how about I use red? I also know that this angle that's right here that I'm coloring in red, this inscribed angle is related to the arc from B to F. That's the intercepted arc by that inscribed angle. So here's what I know is we know the angle from FEB is equal to 1/2 of arc BF. So what has to be then true about those 2 angles is those 2 angles have to be congruent to each other. They are each half of the arc BF. So whatever arc BF is, and it doesn't matter what it is, I just know that both of those angles CBF and FEB are each half of that arc. So therefore those angles have to be congruent to each other. Now I'm going to erase these marks right here just so that it doesn't make things too confusing. But that's why I know those angles, let me just change the color here. Those 2 angles have to be congruent to each other. Let me go back to my orange. So the angle right here at point E has to be congruent to that angle because each of them are half of that arc. So now, here's what I know is true. I know the angle C that's in yellow is the same as the angle C that's in pink. And I know the angle CBF that's in my yellow triangle is the same as the angle CEB that's in my pink triangle. So I already have 2 pairs of angles that are the same in each of those triangles. Therefore, those triangles must be similar to each other. Okay, let me put a little mark or write a little something about why I know this. So just to reiterate, I know that angle C in yellow is the same as the angle C that's in pink. And I know the angle CBF that's in yellow is the same as the angle CEB that's in pink. Then the triangle CBF must be similar to the triangle CEB by angle-angle similarity. Now I can get back to where I was in the first place, and that was, how is that going to help me figure out the lengths here? Okay, well, if I know that the triangle CBF is similar to the triangle, now I'm just to be careful here, C corresponds to C, and then the B that's in yellow corresponds to the E that's in pink, and last, So CEB is the name of the big pink triangle. So my yellow triangle CBF is similar to my pink triangle CEB, okay? And therefore, I can say this. Since the triangles are similar, the corresponding sides must be in proportion. So the side CB corresponds to side CE, and then BF corresponds to EB, and lastly, CF corresponds to CB. Now, this is my equation that will help me figure out what that length from C to F must be. Okay, so that length CF is in this last proportion. That CF corresponds to the side CB in these similar triangles. Now, the thing is I got to get rid of one of these things. And do you notice how the segments BF and BE I don't know the lengths of? Those are the segments that I added to my picture that I never had in the first place. So I'm just going to simply get rid of that ratio. And I'm going to then just substitute what I have and find what I want. So do I know the length from C to B? Yes, it's 6.8. Do I know the length from C to E? Yes, it's 11.6. And then CF is what I'm looking for, X, over the length from C to B again is 6.8. So cross multiply, use your equation solver one way or another, solve this equation, find what the measure of X has to be. So when I put that in my calculator, I cross multiplied, I divided by 11.6, I got this value for X. Now, it doesn't tell me how I should round this, but since all of my other lengths are in the nearest tenth, then I will go with that as well. So the length of CF, if I was going to round this to the nearest tenth, that means that I would be looking at the first decimal place right here, which is a 9. Look to the right of that, that's an 8, so that's going to bump up the 9. So really, if I'm rounding to the nearest tenth, I would have to call this 4.0. And as long as you show your work to justify and it doesn't tell me how to round, then that should be just fine. Okay, so I'm going to make this like a 3-part video series just to kind of keep down the overall length. So here's part 1, this example. I'll do 2 more videos for examples 2 and 3, and then 4 and 5. Enjoy.